For this lab, we focused on forces, and in particular, we looked at work through the use of magnets and IO labs. Our question was, does changing the mass of the cart change the work that needs to be done on the cart by the magnet to cause a repulsion force between the two objects? In our hypothesis, we stated with increasing mass on the cart, there will be more work done on the cart by the magnet system in order to cause a repulsive force.
So in regards to the physical models used for the experiment, we used Newton's first law, which states that an object will remain at rest or maintain uniform motion until acted on by an external force. So in our case, the magnet acts on cart at rest to cause it to move, because otherwise there's no net force acting on the cart that's stationary to move it. Now, Newton's second law states the acceleration of the object is dependent on the net force and the mass of the object. A lower speed/acceleration is going to be observed for heavier carts if the same net force is applied.
For our models, we have a diagram of our scenario, which is a magnet repelling another magnet, which is attached to a cart with a weight on it, and a free body diagram, which shows normal and gravitational force, as well as the force from the magnets repelling.
Herein is experimental design where external repulsive force was applied by a magnet onto the cart and resulting physical observables were measured.
For our force data, we can see the force that the carts experienced when repelled by the magnet. The 20-gram addition caused the cart to experience the most amount of force. Our velocity and acceleration data looks relatively all over the board, but trend lines do show that there is a slight deceleration over time as well as a decrease in velocity over time. Our velocity versus acceleration graphs all show a positive trend within the data, with the 200-gram data having the most positive correlation. Our results show that the car with 200 grams added experienced the most force, and cars with 150 grams were both similar. The 200-gram car experienced the least force. Each car experienced an increasing then decreasing velocity and a very little acceleration throughout the trials. And finally, velocity versus acceleration graphs all have a positive trend showing that work is being done to cause an increase in acceleration and thus an increase in velocity.
So we used our results to calculate the work done by the magnetic repulsion in the magnet system on the cart. And we found that the heaviest cart actually had the most amount of work done on it by the magnet system. And the work energy theorem did confirm this by taking the delta KE, change in kinetic energy for all the carts from initial and final, and using F delta X, which takes the net force times the displacement of the cart. Now, we did have error in results that indicates outlying and unviable data within the trial of 100 grams. Although our results were as expected and the hypothesis was correct as per our data collected, we had many sources of error that rendered this experiment rather unviable, and that was because for trial number 3, as indicated in the previous slide, there was major error due to the person's hand moving the magnet closer to the cart. Now, the same error of moving the magnet closer to the carts to get them to move was more or less apparent in all trials. The lack of uniformity allowed for no proper way to measure the work due to inaccurate delta X. Now, for multiple trials, the video started and ended at different times, with the couple starting slightly after the object truly began moving, and therefore we didn't have an accurate measure for velocity, position, and acceleration. Now, we also did not take into account resistive and other forces acting on the object, which greatly skewed our results due to the fact that the object did end up slowing down, and that was not because of the magnet. Now, although our experiment was inviable due to many sources of error, we have devised several methods of controlling a future experiment much better for a proper experiment. Now, we have to control the distance between the magnet and the cart and make sure the magnet is large and strong enough to immediately cause repulsion as the cart is placed in front of it. Now, we can possibly keep the magnet at the same distance from the cart as well as it moves along its path to keep force constant. Now, we can also take videos with equal parameters to ensure the time frames and no gaps in information such as acceleration, velocity, and position. Now, we can also take into account other resistive forces acting on the cart if F is not kept constant, and therefore we can calculate the minimum force required to move each cart according to the coefficient of static friction to support our arguments. Now, what we should have seen in this experiment was the same work being done by the magnet on the carts, and instead potential differences in velocity. However, not much differences in net force since it's the same magnet system acting on the cart.